Okay, so we just started to talk about polar coordinates. So it's just a different way of specifying a location in two-dimensional space, and it's kind of like with parametric equations. There are curves that are much more easily defined using polar coordinates. So again, if you take Calc 3, you'll be doing things like finding the volumes of spheres, which are not we couldn't do using just calculus of one dimension or one variable. So you would be integrating with respect to um, some other variables that make it a lot easier. Okay, so we said that you can specify, instead of the x and y coordinate, you can specify the distance from the origin r and the angle between the positive x-axis and the radius. That's theta in radians. And as I was saying, you can in polar system you can have more than one coordinate pair that represent the same point on the curve. So I've got this, for example, if I look at a radius of 5, I guess that's what my radius is here. So the radius is 5, and the coordinate, if it was 4 pi over 3, 4 pi over 3 would be here, because you have pi plus another third pi, which would be here. But if I go around, if I add 2 pi to the theta part of the polar coordinate, then I end up in the same place. I just go around one additional rotation. So what I can say is that in terms of r and theta, that the coordinate pair of 5 comma 4 pi over 3 is the same point as 5 comma, what would it be? So you'd have 6 pi, so it'd be 10 pi over 3. So what I did is I added 2 pi to this. I changed it to 6 pi over 3 to get the equivalent of 2 pi. So 6 plus 4 would be 10. And that would be also the same as 5 comma 16 pi over 3. And you could keep doing that forever. Also, you could do it as 5 comma, or actually not 5, but you could do it as negative 5 comma pi over 3. So what I've done there is I've gone to pi over 3, and instead of going in the positive direction, which is you go in the negative direction, and so this point can also be shown by a negative radius. So you can have negative radiuses as well. Now most of the time we'll just do it between 0 and 2 pi. There's not really a whole lot you get out of doing it to all these other ones, but okay, skip all that stuff. That's basically saying the same thing, what I just talked about. Okay. Now, if you want to convert from rectangular coordinates to polar coordinates, you use these two transformations, and you can go the other direction. Going from r theta to xy is easier than going from xy to r theta, and the reason it's more difficult going from xy to r theta is because you have to think a little bit about calculating theta, because it's not just the inverse tangent of y over x. You have to figure out what quadrant you're in, and then determine whether theta is between 0 and pi over 2, or pi over 2 and pi, or pi and 3 pi over 2, or 3 pi over 2 and 2 pi. Whereas if you go this direction, if you go from r theta to xy, you just plug it in your calculator and you don't have to worry about it. So there's two things you can do. One is to actually convert the numbers, so I can give you the xy coordinates and then you can calculate the r theta coordinates. There's also converting an xy equation to an r theta equation, or an r theta equation to an xy equation, which is a little more difficult. So let me erase that because that's the answer. But let's say we want to go from the xy coordinate of -2, 5 to the r theta, equivalent r theta coordinate. So we're going to use these relationships, but when we figure out theta, what we're going to do is use the reference angle concept, because we'll take the absolute value of these two, so that when we take the inverse tangent, it ends up being in the first quadrant. And then we can look at the sign, or we could just plot the points and figure out which quadrant it's in. And if it's in the second quadrant, we're going to take the reference angle and subtract it from pi. And if it's in the third quadrant, we'll add it to pi. And if it's in the fourth quadrant, we'll subtract it from 2 pi. So let me sit down here. So the r part's easy. So r is going to be equal to the square root of -2 squared plus 5 squared. And r is always going to, I told you r could be negative, but when you do this, typically you let r be positive. Well, the answer is going to be equal to the square root of 29. There's no point in. So 4 plus 25 is 29. And then when to calculate the theta, what we'll do is we'll calculate the reference angle, which is going to be the inverse tangent of the absolute value of y divided by x. So if we make sure our calculators are in radians, which mine is right now. So we're going to take the inverse tangent of 5 divided by 2 instead of 5 divided by -2. So we get the reference angle is 1.190 radians. And we could, if we wanted to, convert it to some percentage of pi. If we wanted to, you don't really need to do it. You can just leave it as radians. So either one of these is okay. So I'm going to go ahead and just do the other one just for completeness. So if we take 1.1009 divided by pi, we'll get 0.379 pi radians. Okay, now if I plot the point, -2, 5, I see it's in the second quadrant. Or I could say, well, when I have a negative x value and a positive y value, it's going to give me in the second quadrant. So I don't have to think too hard about that. I just look at it, second quadrant. So as a consequence, the theta is going to be pi minus the reference angle. So I guess in this case, it might be easier to do it in terms of some decimal equivalent of pi. So 1 minus 0.379 is 0.621 pi, or I guess you could just take 3.14159, or just pi, and subtract 1.190. So another way to do it would be take pi minus 1.190, which would be equal to 1.95 radians. So these are the same thing. I'm just doing one as a decimal percentage of pi. So the answer is going to be equal to the square root of 29, 0.621 pi, or the square root of 29, 1.95. Either one's okay. Let me just double check, make sure I didn't make a mistake. Yep. Okay. So that's easy. Oh, that's the only hard part is just, as I said, is to remember to just don't take the inverse tangent and worry. Take the inverse tangent of the absolute value, and then figure out what quadrants you're in based on the xy coordinates. Let me just add. So let's do another one, but we'll do it the other way. So let's say I give you 4 comma 5 pi over 3. Convert to rectangular. So all you have to do is x is equal to r cosine theta. So it's going to be 4 times the cosine of 5 pi over 3. And y is going to be equal to r sine theta 4 sine 5 pi over 3. And I'm just going to stick it in my calculator. 4 times the sine, 5 times pi divided by 3 is equal to negative 3.464. Oh, that's this one down here, sorry. And this one is 4 times cosine 5 times pi divided by 3, and I get 2. So the corresponding xy coordinates are going to be 2 comma negative 3.464. Okay. So it's not anything different than you did in pre-calculus as far as knowing how to do that stuff. And let's just think about this. So if we put just to double check, if I draw a circle with a radius 4, so this is 4, and I go to 5 pi over 3, so 5 pi over 3 would be right down here. And as a consequence, the y value should be larger in magnitude than the x value, which is true. It's negative, which is true, and x is positive, which is true. So it all makes sense if you draw that kind of using the unit circle kind of concept, even though it's not a unit circle, it's a circle. Okay. Now, let's see if I just did that, something like that. Just did that too, so let's skip that over. Okay, so the next one is how do you convert from an equation that's in rectangular coordinates to polar coordinates. So if I looked at this equation, x squared plus y squared equals 4, you might say, well, I know it's a circle of radius 2, but what you would do, let me erase all this stuff because it's start all over again here. Okay, so the substitutions we have is that x equals r cosine theta and y is equal to r sine theta. So we can just plug that into there. So what we get is r cosine theta quantity squared for x squared and r sine theta squared for y squared, and that equals 4. And you would then have r squared cosine squared theta plus r squared sine squared theta equals 4. You could factor out the r squared, you get r squared. I'm going to change the order. Sine squared theta plus cosine squared theta equals 4. But sine squared theta plus cosine squared theta equals 1. Therefore, you get r squared equals 4, or r equals, I guess, plus or minus 2, which is true, but we would probably just think of it as 2. So the xy equation for a circle is that, and the r theta equation is just r equals 2. It's all the points that lie 2 inches or 2 units from the origin. So obviously this one's a lot simpler equation than that one is. So we might want to use the r theta form of the circle sometimes, which we do. Okay, so there it is. Okay, let me erase all this stuff. Okay, so here's another one. xy equals 4. What is that? That's going to be y equals 4 over x, which is the reciprocal function with it's just a stretched reciprocal function. So let's see what, as you saw, there was a lot of stuff on there. Well, it's not quite as simple. So, and I know this one turns out to be, so hopefully I'll remember how to do this. So let's try it again. X equals r cosine theta. Y equals r sine theta. So let's plug it in and see if I can remember how to do this. So we get r squared sine theta cosine theta equals 4. And really all you need, if you look at this, I've solved this equation for y. Typically, in these kinds of equations, you solve for r. So here we have just r equals 2. It's like x equals 2 or y equals 2. It's the simplest form of an equation in polar coordinates. So I could just say r squared equals 4 divided by sine theta cosine theta. And I could take the square root, but I think there's I forgot to bring my book today, but there's probably, anybody bring the book today? Do you have that sheet? Yeah, that's all I need is I need the trig identity sheet. So there's probably some trig identity that we might be able to use. Thank you. So really the only one that we have is this sine theta cosine theta equals, well, here I'll write it down, the one that looks like it might work. Sine of 2 theta is equal to 2 sine theta cosine theta. So I could solve for sine theta times cosine theta is going to be equal to 4 divided by, and then I'm going to have, this is going to be equal to sine of 2 theta divided by 2, which is 8 divided by sine of 2 theta. And so you get r is equal to the square root of 8 divided by the square root of sine 2 theta. Makes me believe there's some other better way of doing this. It is a function of theta. R is a function of theta, but it's not exactly what I was hoping for. Let's see if I can remember. Let's see if there's anything. What I might do is let's see if I've got anything here to help me out. No. I can always undo and see what I had written last time. Actually, what I'm going to do is, I always mess this one up. I only do it once a year, and I always forget. So what I'm going to do is I'm just going to open up last year's notes and try to figure out what I did wrong. By the way, you guys all looked really good. I saw your prom pictures. I guess your dad posted his last night or something.
Yeah, I posted all of mine
On
and
your,
tagged him in it.
it tagged him in it. Oh, is that what it was? Okay, yeah. Martha showed me those this morning. And I saw yours because of Wyatt. He was tagged in stuff. Okay, let's see what I... Here it is. Oh, that looks about what I had. Okay. Maybe there isn't any better way of doing it. Okay. Yep. Okay. That's about as good. Okay. Let's actually plot these, because one thing you can do is you can plot them both ways. So if we plot in 2 dimensions the equation in explicit form, well, implicit, we could do that. So that was xy equals 4, and we graph that, and it looks like the reciprocal function. Okay. We can also do the polar form. So the polar form would be the square root of 8 divided by the sine of 2 times t, and we let t go between 0 and 2 pi, which is 6.339 approximately. Oh, that doesn't look the same. So what did I do wrong? Oh, I forgot to do the square root. Yep. So let's fix that. Okay, so it was square root of 8 divided by the whole thing divided by sine of 2 times t. Was that the one? Make sure I did that right. Sine of 2t, yeah, okay. 9, 5, 6, 6. There we go. So you can see when I did it correctly, it just wrote over the same, this particular curve. So it is true. I guess that's as good as it gets. Okay, so that's so what you basically saw is we substituted in for x and y r cosine theta and r sine theta, and then we solved for r. And if we could use any kind of trig identity, the first one was we used the Pythagorean identity, which made it really nice. The second one, it wasn't, it's slightly better, but if I just left it as sine theta, cosine theta, it probably would have been just as fine as far as the result. Now, when it comes to going the other direction, a lot of times you will use the r squared is equal to x squared plus y squared. And that's basically what I did here. So if you start with the polar equation r equals 3, and we have x squared plus y squared equals r squared, what we do is we take this and square it. So you get r squared equals 9. And then for r squared, you put in x squared plus y squared. And so you get x, that's the rectangular form. If there was a theta in there, we probably would use the arctangent somehow or another. Let's do another one here. Okay. So here is one r equals 3 secant theta. So the question is, how do we do that, right? I just told you. So we could square both sides. You get r squared is equal to 9 secant squared theta. And then just like before, you can use a Pythagorean identity to rewrite secant squared in terms of tangent squared, I think. So let's see what we got here. So if I put secant squared is equal to 1 plus tangent squared theta. So then I can, for r squared, I can put x squared plus y squared. And for the tangent of theta, I put y over x, and I square it. Okay? X squared plus y squared for r squared, x over y for the tangent of theta, And you might think that looks pretty hard. I'm not sure what that looks like, but let's try finding a common denominator here. So we're going to combine these two into one fraction. So we get x squared over x squared plus y squared over x squared. And then you can add the two numerators. You get x squared plus y squared over x squared. But you'll see that I have x squared and y squared on both sides. So I'll get, if I divide both sides by this, it disappears, and I get 1 is equal to 9 over x squared, or x squared equals 9, or x equals plus or minus 3. This is one I do remember. Okay. When I first did it, I'm like, well, I didn't know what to do. But so ultimately, this equation r equals 3 secant theta, which is the r theta version of a curve, is actually the same as just a vertical line, two vertical lines, one at -3 and one at +3. And we can prove that by plotting them out, showing you that it actually does work. So let's close that. So if I put in the equation, the polar equation, which is r equals 3 secant theta, and I go from 0 to 2 pi, you see I get a vertical line at x equals 3. Now I don't want to get one at -3, and I'm not sure why that is right off the top of my head. Let's just try going to, I'm sure there's some good explanation for it. I was just going to try something like 2 pi and see if I get anything different. No, still you get the same thing. So anybody have any idea why it only plots the positive when I take the square root of that thing, square root of 9? Well, I think if you look back at the original, maybe if I went -pi/2. Because you think about the secant of theta. The secant of theta is, well, it's got some vertical asymptotes in there somewhere, doesn't it? I don't know. I'd have to plot that. Let me just try -pi/2 just for the heck of it. See if that works. If not, I'll have to think about it because I can't. Okay, so we're going to go from 3 secant theta. We'll actually go, I think you could go from -pi/2 to +pi/2 because the secant of 0 is 0 and then it kind of goes like that. So let's go from what's pi/2, 3.14159 divided by 2, 1.57. So we'll go to -1.57 plus 1.57, and we'll plot that. Nope, we still end up with just one of those two curves, so don't know. Okay, so that's some examples of going between rectangular to polar and polar to rectangular. Now the last thing is finding the tangent lines to r theta equations, but the tangent lines are still going to have a slope which involves y over x. So the way this works is that we know that the conversion from polar to rectangular is like a parametric equation. But instead of there being one parameter, there are two parameters. There's r, which is a parameter, and theta, which is a parameter. And you can have more than one parameter in your parametric equations. If you remember when we were looking at this graphing program and we go to polar, you'll see that somewhere here, well, this one doesn't do it. Oh, parametric, sorry. If you go to parametric, you'll see that you can have both x as a function of theta, it says t, but I think you can actually have as a function of two variables. Maybe it's three-dimensional. Let me just check it. Hold just a second. I know it shows it in here. 3 dimensions equation. Parametric. Yeah, you can have both t and u. So you can have parametric equations that have two parameters. So we do in this case. But we also, the polar form of the equation, instead of y is equals a function of x, we can have r as a function of theta. So we can write the curve r as a function of theta as a two parameter equations for x and y, where theta is the parameter. Okay, so actually I was lying there. In this case, theta is the parameter. So the way it works is we have, so of the parametric equations, you have r, which is a function of theta, and then you have theta in terms of the second part of the conversion between polar and rectangular coordinates. So where you see f of theta, the cosine theta, that's really this, because r is a function of theta from this relationship. So this relationship is converting from polar to rectangular. This is the relationship between r and theta, which is the functional relationship. Likewise, y equals r sine theta becomes y equals f of theta sine theta. And what we did in section 10.3 is we said that dy dx, the slope of the tangent line, was equal to dy dt divided by dx dt. What we do in this case is, instead of the parameter is not t, but the parameter is theta. But we have a product. We have the product of f of theta times cosine theta. So we have to use the product rule to evaluate dy d theta, because it's not just theta by itself, it's two parts. So you're going to use the product rule. Yeah. So all we're doing here is replacing t with theta. Okay. So we use the product rule to differentiate the conversion from polar to x and polar to y. So the first one, the second one, dy d theta, you take the first term, which is f theta, and multiply it by the derivative of the second term. The derivative of the sine is the cosine. And then you take the derivative of the first term, which is f of theta, so it becomes f prime of theta, times the second term, which is the sine of theta. So that's what dy d theta is. It's the relationship between r and theta for the curve times the cosine of theta, and then the derivative of the relationship between r and theta times the sine of theta. And you can do the same thing for both for x and y. So dx, yeah, up here I'm taking the x equals f of theta cosine theta. So you take the first term times the derivative of the second. The derivative of the cosine is negative the sine. Then you take f prime of theta times. So this is the derivative of the first term times the second term. So as it says there, so for polar coordinates, the slope of the tangent line, dy dx, is equal to f of theta cosine theta plus f prime of theta sine theta divided by negative f of theta sine theta plus f prime of theta cosine of theta. And if you're looking for the case where you have a horizontal tangent line, so that would be, like if you were at the top of a circle or the bottom of a circle, you'd have a horizontal tangent line, or any curve, then all you have to do is set the numerator equal to 0 and figure out what values of theta that occurs at, where theta is the parameter in this case. So it says if dx d theta, which is the numerator, or wait a second, actually it says dx d theta can't be 0, because if that's true, then you get an indeterminate result, or an undefined result. And if you have a horizontal tangent line, that's when the numerator equals 0 and the denominator does not equal 0. If you get vertical tangent lines when the denominator is 0 and the numerator is not 0. Okay, so these are some special cases. In general, though, if you want to find the slope of the tangent line to a r versus theta curve, then you have to evaluate this more complicated expression. So let's look at this example. Find the equations for the tangent line at the given value of theta. So this is my r as a function of theta. And what I need to do is I need to plug it into this equation. So the f of theta is equal to 3 times 1 minus cosine theta. That's r. This relationship, r as a function of theta, is f of theta. So we take we need the derivative. We need the derivative here to evaluate it. So f prime of theta is just going to be equal to 3 sine theta. Because the derivative of 3, if I multiply this out, I'll get 3 minus 3 cosine theta. So the derivative of 3 is 0, and the derivative of this is negative 3 times the derivative of the cosine, which is negative the sine, so the negatives cancel out. So that's f prime of theta. So what we can say is that the slope of the tangent line, dy dx, at any value of theta, we're going to evaluate it later at pi over 2, is going to be equal to this thing, f of theta, 3 minus 3 cosine theta times cosine of theta plus f prime of theta, which is 3 sine theta times sine theta. And then we divide that whole thing by negative f of theta. So it's negative 3 times 3 cosine theta times sine theta plus f prime of theta, which is 3 sine theta times cosine theta. Now, believe it or not, this is going to simplify. So let's just multiply everything out. So we get 3 cosine theta minus 3 cosine squared theta plus 3 sine squared theta, all divided by negative 3. Maybe it doesn't simplify, but we're going to evaluate it. So we got negative 3 sine theta, that's this times that, plus negative times a negative is a positive, so that's 3 sine theta cosine theta plus 3 sine theta cosine theta. Yeah, I don't think it actually simplifies it. I think we just need to evaluate it. So we're going to evaluate at theta equals pi over 2. So we'll get 3 cosine pi over 2 minus 3 cosine of pi over 2 squared plus 3 sine of pi over 2 squared divided by negative 3 sine of pi over 2 plus, well, these two do combine, 6 times the sine of pi over 2 cosine pi over 2. So I've just combined the last two terms here. 3 plus 3 is 6. And, you know, pi over 2 is going to either be, it's going to be either 0 or 1. The cosine of pi over 2 is 0. So remember, cosine of pi over 2 equals 0. The sine of pi over 2 equals 1. So we can plug those in there. So we'll get 3 times 0 minus 3 times 0 squared plus 3 times 1 squared divided by negative 3 times 1 plus 6 times 1 times 0. And you see everything drops out. These all go to 0. So you just end up with 3 divided by negative 3, which is negative 1. So that's the slope of the tangent line for this original r versus theta. 3 times 1 minus cosine theta. And if we wanted to know what it was at any value of theta, we would just plug in theta and get the value. Of course, at any other value of theta, it's probably most other values of theta, it's not going to be quite as simple a calculation. So we're going to plot this just to prove that it actually is equal to negative 1. So let's find my graphing program, which apparently I closed. So let me open this thing up. So let's see what the function looks like first. And I'm only going to plot it to pi over 2 because then I'll know exactly where it stops. So I'm going to go to polar coordinates, and the function was 3 times 1. What was it? 3 times 1 minus cosine theta. And I'm going to go between 0 and pi over 2. Pi over 2 is 1.570795. And I've got an extra thing in there. 0.5701, 1 point. And I need to zoom out a little bit here. Zoom out. Page down. So what it's saying, this must be when theta equals pi over 2. This is when theta equals 0. So you can see at this point, this curve has a slope of negative 1, which agrees. And just to prove that that's really true, what we can do is we can draw a line that has a slope of negative 1 that goes through 3. So if we do negative x plus 3, that should be a good curve. And you can see that it does. It is tangent. This curve, which has a slope of negative 1, is tangent to this parametric equation or this polar equation. And let's actually do the polar equation just to see what it looks like if you go to 2 pi. Just curious. 1 minus cosine theta. So 1 minus cosine t will go between 0 and 2 pi, 6.29. That's wrong. Something's wrong. That's a circle. Let's try it again. 3 times 1 minus cosine t. 6.29. Yeah, so that's what it looks like. So the actual curve, I don't know what you would think that looks like. It's like somebody's behind, I think. But anyway, the point is that we did correctly predict the slope of the tangent line at pi over 2, which is that particular point. So yeah, it's pretty complicated. And here's some homework for section 4. So what we've learned is how to convert from, and this is due tomorrow because we're running out of time. So we learned how to convert from rectangular coordinates to polar coordinates when we're talking about the actual coordinates, also from polar coordinates to rectangular coordinates. We learned a little bit about how to convert an equation that's in rectangular form into polar form and one that's in polar form into rectangular form. And we've learned how to find the slope of the tangent line to a curve when the curve is a function, r is a function of theta instead of y is a function of x. What I'm going to, if you've watched the review, you'll see that I think the only thing that I ask you to do out of this section is just convert coordinates from one to the other. So I'm not going to ask you to. Sometimes, you know, it's a little tricky. It's kind of like it's like trig identity. Sometimes you see it immediately, and sometimes you don't. So, and then this derivative stuff is pretty complicated. I just wanted to quickly go over it, just so you know that if you do want to find the slope of the tangent line for a r versus theta curve, that you can do it. It's just a matter of using the transformation equations as well as the product rule. And you might have a homework problem that uses that, but don't worry about the test as far as understanding that completely. Okay, so we're going to go back to section 1 here and do as much as we can in the next day and 10 minutes. So section 10.1 deals with conic sections, and we said those were parabolas, ellipses, circles, which are a special kind of ellipse, and hyperbolas. And they're called conic sections because you take two cones that are rotated around one of the axes, probably the z-axis, and then you take a plane and you cut that plane at different angles with respect to this cone, and the shapes of the intersection between the plane and the cone is depending upon what angle that plane is at. You'll get a parabola, an ellipse, or a hyperbola. So that's why they're called conic sections. But so that's what we said the other day. So this is a parabola, and in terms of analytic geometry, you define the parabola differently than we think of in terms of algebra or pre-calculus. In pre-calculus, it was basically y some function that was y equals something x squared, and it still is. But the official definition of the parabola is you have a horizontal line, which is called the directrix, and you have a focus of the parabola. And then every point on this parabola is defined such that the distance between the directrix, which is this horizontal line, if you take a perpendicular projection from this horizontal line up to here, that the distance from the focus to that point is the same as the distance to that point to here. So the distance from Q2 to P2 is the same as the distance from the focus to P2. It doesn't look like it. It's probably because it's not drawn to scale or it's stretched out incorrectly, but that is the truth. Okay. So when you're at the vertex, the distance from here to here is the same as the distance from there to there. So it's more of a geometric explanation. So I'm going to just write this out. So a parabola is defined by a point, the focus, and a line, the directrix. Okay. The distance from a point on the parabola to the vertex, or I mean the focus, is the same as the distance from the same point to the directrix. And this is, we'll say it's the shortest distance. So the shortest distance from here to the directrix is always going to be a line that's perpendicular. So you can see these are all perpendicular. So the distance from the focus to a point on the parabola is the same as the distance from that same point to the shortest distance from that same point on the parabola to the directrix, which turns out to be a perpendicular line. So if I picked a point here, and I looked at the distance from here to some other point on the parabola, and I measured the distance from that same point down to here, these two distances would be the same. And all of those, the locus of all those points, meaning all, I don't know what the official definition of locus is, but it's basically all the points that satisfy that requirement define the curve. Now it turns out that the parabola does have the form that we're used to looking at, but that's the geometric. So let me put this on one page. So there's two standard forms for the parabola, depending upon whether you have a vertical axis or a horizontal axis. The one that we're used to is the vertical axis, y equals x squared. So the standard form is the quantity x minus h quantity squared is equal to 4p times y minus k. And once you get the equation into that standard form, the values of h and k are the coordinates of the vertex. The equation of the directrix is a horizontal line, y equals, and it's equal to k, which is the y coordinate of the vertex, minus p. So that's that distance. P is the distance from the vertex down to the directrix, and also the distance to the focus. Okay, so that's the equation for the directrix. And then finally, the coordinates of the focus point are equal to the x coordinate of the vertex, and instead of taking k minus p, you take k plus p, because they're going opposite directions. The directrix is this way and the focus is that way. So that's why the sign changes. So the whole idea here is to take an equation that's not in standard form and then to manipulate it so it is in standard form. And once it's in standard form, then you can define all the appropriate or important parameters associated with the parabola. The vertex, the line that defines the directrix, and the focus. And once you have that, then you can sketch in the parabola by using that information. And there's an equivalent one for a horizontal axis. So that would be a parabola that looks like this, which is not a function. So, but you do the same thing, except you'll have x and y switched as far as the standard equation, which I'll show you next time. So that's it for today, and we'll see you tomorrow.